Hello everyone. In the previous clip, I discussed about the fundamental of switch mode power supply, and I also mentioned that there are many different circuit design or topology for a switch mode power supply. So in this clip, we will discuss different type of topology or design for the switch mode power supply. So this article I will base on the Texas Instrument power topologies. You can check out their website ti.com, the many article. And once again, my appreciation to Texas Instrument for giving us many great power electronic articles. So now at first, we talk about the non-isolated type of converter. And the most important one is the buck converter. This is a fundamental buck converter. The input of the buck is always higher than the output of the voltage. So that's the simple rule for a buck converter. And the circuit is very simple. Only one FET, one diode, and an LC filter running at high frequency. All switch mode power supply running at high frequency. So this type of converter can run from a very low power, a few watts, up to a few hundred watt or even 500 watt or more easily. If you're running a circuit at high current, I would recommend that you move on to the next one, which is a synchronous buck converter. It's very similar to the buck converter on this one. The only thing different is that the diode is replaced by a FET. The FET it has very low RDS on, so with high current it is more efficient than the regular buck converter. Now we move on to the next topic. The boost converter. The boost converter is similar to the buck, but the input now is always lower than the output voltage. And once again, the circuit is very simple. It has an inductor, capacitor, the switching FET, and the diode. You can also replacing the diode with a FET to make it more efficient, similar to the buck. Then we have another one, which is a combination of the buck and the boost. This circuit here we call inverting buck boost. And with the buck boost type, your input voltage could be either higher or lower than the output voltage. The only thing special on this circuit is the output is a negative voltage compared to your input voltage. So we call it inverting buck boost converter. So here's another group of different type of buck boost converters. We have the Sebic converter, a choke converter, and zeta converter. It's getting more complicated because of adding the capacitor and this type of converter. And with this type of one, you can, the Sebic converter, your output is positive compared to your input. For the choke converter, your output is negative voltage compared to the input. With zeta converter, the output voltage is the same potential with the input voltage. Now we move on to a different type of class. The type we call a non-isolated, the isolated type of converter, which use transformer in the design. If you look at this one, this may be not quite fully isolated. The part of this one is actually a synchronous buck converter. However, they changing the inductor, they're using a couple inductor to create another output voltage. So you can build multiple winding on top of this one to keep creating 2 or 3 extra outputs on top of this one, giving the name as a fly buck converter. So this is not fully isolated for this circuit here. Now we move on to the actual with the real transformer in them. The flyback converter is one of the most popular design. For the medium power from a few watt to maybe up to 100 watt, you can use the flyback converter. It is a very simple, involving with a switching FET, a transformer, diode, and output capacitor. Very simple design. Your input could be 110 volt AC source up to 240 volt, and the output could be anywhere +5, +12, 15, or can be even higher. You can build a high voltage out of this one. So this is one of the most popular. Another design that's similar to the flyback, we call it a two-switch flyback. If you look at the diagram, it looks exactly similar to the flyback converter, except that we're adding a transformer and 2 diodes in this scheme. This is a little bit more complicated. Your drive circuit will have another FET, which is a Q2, stay on top of the transformer. So this is a floating drive circuit, which makes it more complicated. The next class of isolated type of switch mode power supply is we call a forward converter type. The single end switch forward is one of the most popular one for this type of design. One of the issues with this type of design is if you have a 220 volt AC, and when you're converting to DC, it could be around 310 volt. Your voltage across Q1 is twice of the input. So we could see at somewhere around 620 volt, plus some leakage voltage ringing on top of that. So it could creating very high voltage across Q1. So this design is not suitable for the input source of 200 volt something. Maybe the low type of bus, 48 volt, 100 volt bus. And the circuit is also pretty simple. You have a switch FET, a transformer, 2 diodes, and an LC filter. Now we move on to a little bit more complicated, the 2-switch forward. So in this type of circuit, it's similar to the flyback we see before, the 2-switch. You're adding another Q2 on top of the transformer. So with this, your transistor does not see twice the input voltage anymore. So each transistor will see only the same voltage as the input voltage. So that's a big advantage compared between the 2-switch with the single switch. However, the circuit drive would be more complicated. And the last one, which is another really famous one, and many people use it, the active clamp forward converter. We replacing the reset winding here with this active reset winding through the capacitor C1 here. Now let's move on to another topology, the push-pull converter. A push-pull converter is also very popular. The drive circuit is simple because of the 2 FET that reference to ground. So your drive circuit is very simple, very straightforward. You can drive it, and the reference is from the mass, from the ground. The transformer is a little bit more complicated, as you can see it. It's more complicated compared to the other type of flyback or forward. On your secondary side, you will have 2 diodes in this case, and an LC filter circuit. So this type of push-pull converter will be designed for a medium power of circuit, like I would say somewhere 100 watt or up to a few hundred watts, 200 or 300 watts. On the right side, you will see something more complicated. We call it a Wayne push converter. This is used for space application, highly efficient, and design seems like to be more complicated compared to the push-pull. And you can see that the difference is on your secondary side, you do not have the inductor there anymore. And everything that they're moving that inductor back to the primary side. So if you have multiple output, you do not need to design every inductor for each output. You only have the inductor on the primary side. But this type of circuit is different. The inductor is a coupled inductor. It's feeding the current for every switching cycle directly to your secondary side. So some people also call this as a current-fed push-pull topology. Now come to the last and one of the most important in power electronic for high power DC-DC motor, DC-AC inverter, EV control circuit. The push converter, they have like 3 different types. The first one is the half push. The half push converter handles the medium power. And the circuit is a little bit more similar than the full push, only need 2 FET, a simple transformer with only 1 winding on the primary side. And the secondary side will have a switching diode and LC filter. Now we move on to the second one, which is more power. If you're running somewhere 500 watt up to 1000 watt, the full push is very compatible for those high power design. Now the circuit is getting more complicated. Your primary switch has 4 switches, and the rest of them is very similar. You will have a transformer with 1 winding and 2 secondary winding in this case. Also we have LC at the output. However, the drive circuit is far more complicated. The last one, which is based on the full push design, but the phase shift, the duty cycle, the phase is shifted. And the duty cycle changed due to the phase angle change within the switch. So everything looks pretty much the same, except that the phase for the duty cycle doesn't really synchronize like the case that we see in the full push. However, that will make the current will come up when there is no voltage there. So similar to a ZVS type of circuit, zero voltage switching. So this is the end of the introduction of different topologies for switch mode power supply. So depend on your design requirement, the power, you will need to be able to choose it, which one is suitable for your design. So once again, thank you for watching, and I hope you learned something from this.